So we're going to start with these solids forming as one of the key drivers and precipitation reactions. I had to do a double take on this video because I couldn't say precipitation somehow. So precipitation reactions happen when you mix two aqueous solutions. So it could be a yellowy translucent solution and a clear solution, and you make a solid. And it's going to kind of be a cloudy mess for a bit, but eventually it will precipitate like rain falling from the sky. It precipitates, it falls to the bottom of the vessel that it's in. So in all precipitation reactions, the ions of one substance are exchanged with the ions of the other. That is what we're talking about with the double displacement reactions. At least one of the products formed is insoluble in water. And so we talked about how things that are aqueous solutions, right, are AQ, that's what happens when they're soluble. That's what happens when they dissolve. If something is an ionic compound, not all ionic compounds dissolve, we would say they're insoluble, and we give that physical state as an S in our chemical equation. And so these couple examples here are ones for us to do. And so this is an example of what the reaction would look like. And this is sort of an illustration of what's happening on the ionic level. And so before the solution, we have before the reaction, all the ions are in solution. After the reaction, we have a precipitate formed at the bottom of the beaker. So let's start out with this. We've got a bunch of different graphic illustrations. We also have the words. And what we're going to come up with down here is that chemical equation. So potassium chromate would be KCrO4, but chromate is a 2 negative and potassium's a 1 positive, so it's K2CrO4 aqueous. That means that it's a solution, is added to a colorless barium nitrate solution. So barium and nitrate. Nitrate is -1, barium is a +2. So crisscrossing these up, we'd have the formula for barium nitrate like that, and it is a solution, so it's an aqueous solution. It's a homogeneous mixture. So before we have all of these things in solution, after we have the barium chromate visible at the bottom of the solution or of the beaker. And so barium and potassium have swapped anions. So barium is now with the chromate ion, as is evident from our little illustration here. And that's solid, that's the precipitate, that's the insoluble ionic compound. And then we still have the other half of this. So finishing up the double displacement, we'd have the potassium then bonded with the other anion, so potassium nitrate. And that is still aqueous. That's still those ions in solution. We have the nitrate ions in solution and the potassium ions in solution. We're almost done with this. The one thing we haven't done yet is balance it. So I'd start with the metals, doubling up that. Barium is fine. The polyatomics that stay together, chromate is fine, and the nitrate checks out. So that would be the balanced chemical equation for the precipitation reaction that is illustrated above. Let's do the next one. So we've got a bit more of an illustration. We have the words. So we have potassium chloride and silver nitrate going to be mixed together. So they're both aqueous solutions. So potassium chloride solution is going to mix with silver nitrate solution. Go ahead, double check the combining capacities of the metals and the anions and that polyatomic. You can always pause this if I'm going too quick. And that's going to make, we're going to swap the partners here. So we're going to have potassium nitrate. And you can see that that's still in solution. The precipitate would be at the bottom of the beaker. And so our precipitate here would be a solid, and it would be AgCl. And again, it's the precipitate, so it gets the S put after the formula. And so that's kind of the nuts and bolts of a precipitate or precipitation reaction and illustrating this idea of a double displacement reaction. Now, it's all fine if we get pictures of all of these that show the precipitate, but there is also a set of rules that govern if things are soluble or not. So in your formula pages, you have a table that allows you to predict if an ionic compound is going to be soluble or insoluble. So back to your formula pages, right here, this solubility chart is basically used to determine if something is soluble, and so that would be an AQ, or insoluble or a precipitate, and so those would be solids. And so basically this works by dissecting out after you've got that double displacement reaction done. So that you'd start with a negative anion and then take a look at which one it is and then what it's grouped with and kind of follow across the chart this way to then to determine if it's soluble or insoluble. I think it's important to use this chart so you understand how it works. So that's exactly what we're going to do. There's a couple little notes on these. So start with the anion first and then the cation, kind of following it across the chart this way. There are some to watch. So the alkali metals, those would be in the first column of the periodic table. So it doesn't list them all specifically, but we'd have to know that sodium and potassium and all that, they're an alkali metal. The other thing is the all others to watch for. And so those are just things to keep your head on straight about when you take a look at this solubility chart. So we're going to use the solubility chart to determine the physical state of each of the ionic compounds below. So we're going to start with calcium chloride. So when I look at this, I'm going to find chloride as my anion, and then I'm hoping to find calcium. Now calcium is not as a cation spelled out down here, so calcium would be in the all others, which means that calcium chloride would be aqueous, or it would be soluble, or AQ. As you work through, this is the way it goes. I'm going to do one more and then I'm going to put the answers up because I think it's important for you to do. So we had lead to bromide. So we'd find bromide as my cation, and then I can see the lead as the cation, which means that this would form a precipitate. This would be an ionic compound that was insoluble or low solubility. And so this would be a precipitate, or it'd be insoluble. And it would have an S after it in a chemical equation, because that's what it says, determine the physical state of these ionic compounds if they were in water. And so I'm just going to go through and do these ones up. You can take a look at the chart. If it helps to put the other words in there, then that's cool. Sometimes that helps people. But the bottom line, what we're trying to do is get the physical state of each one of these using that solubility chart as our predictor. So we're going to practice doing about 4 of these ones, these precipitation reactions. We can go back and look at those rules. I think sometimes it's easier to see these. So these are my reactants, and I'm going to practice the pattern of a double displacement reaction. So the lead is now going to combine with the chlorine. The combining capacities of this, I can see that it was the lead 2 nitrate. So lead 2 would combine to make PbCl2 as my compound, so lead 2 chloride. I know it's going to have some state, but I'm going to come back to that. I'm going to finish up the pattern of double displacement. So the other cation goes first, and it mixes or pairs with the other anion. The combining capacity of calcium is 2 plus, and nitrate is 1 minus. So that would be, crisscrossed up, the formula for calcium nitrate. Now I need to take a look at my solubilities chart. If I take a look at the solubilities chart, starting with the anion, I think we already did this one once, following across, I would conclude that this was the precipitate. It would be solid. And similarly with this one, I would find nitrate as my anion and take a look and find out that all nitrate compounds were soluble. So that would be an AQ. That would still be in solution. For all of these, we're going to practice writing a balanced chemical equation, starting with the words as the reactants. So copper, 1-acetate. If you're doing this, watching the video, you might want to pause it just so you can kind of catch up with the nomenclature, is going to mix with sodium bromide. And I'm taking the time to think through those combining capacities to get to this answer. Then I'm going to practice this pattern of double displacement. So copper is now going to mix with or bond with the bromine, making copper 1 bromide. Don't know the state on that one. And the others are going to fill in the rest of the pattern of that double displacement. So sodium acetate. I always run out of room. Checking the states of these, I would find that my copper 1 bromide is my precipitate, and my sodium acetate is my aqueous solution. It's still soluble. Last ones, I'm going to just put the answers up. There was a little note in the instructions, so if you get to this one without checking, there's a wrinkle with this one. The double displacement is the pattern that I'm using, so H, nitric acid, and silver chloride. If I look these up on the solubilities chart, that's the next step, I would find that my nitric acid is aqueous and my silver chloride is my precipitate or is solid. Last one, sulfuric acid and copper 2 nitrate. Solutions, that's why they're both aqueous. Practicing this double displacement reaction, so it'd be HNO3, swapping anions and cations. Don't know the state on that one yet. And then copper 2 sulfate. When I take a look at this one and follow through on my solubilities chart, that one's going to be aqueous and this one's going to be aqueous. You followed the double displacement reaction pattern absolutely fine. In this one, there's going to be no reaction that's visible. And the reason that there is no reaction in this is that there isn't that driving force of forming a precipitate. So no precipitate formed. So this is the first time you're able to make a prediction, understanding nomenclature and understanding balanced, oh, didn't balance it, my goodness, balanced chemical equations to predict if you're going to have a chemical reaction or not, just given the reactants. And then understanding from there.